So all that said, we're going to get into the notion of vector spaces here, and we're going to do this very abstractly. This is the correct way to define vector spaces, but it does often feel like you're left out kind of to dry as you're trying to learn how to read these math definitions. So the definition of a vector space is this ordered quadruple here. So I want you to practice writing this out. So go ahead and just write out, the vector space V, the field F, the symbol plus, and the symbol multiplication. Okay? So this is going to be the set of vectors. This is going to be what we call the underlying field. And then we have the notions of vector addition and scalar multiplication. Okay. So we will quickly drop this long kind of weighty way of talking about a vector space, and we will just use a symbol like this V here that I've given you for a vector space. Okay. Then what I said before is we talk about the things that belong to this set right here as vectors. And again, folks, I'm being very abstract here. So you're going to find this a little bit disconcerting, and hopefully after we've given the definition, then looked at a couple of examples, it'll begin to clarify. So for every u, v, w, and v, so here I've got 3 vectors in my vector space, and here I've got 2 elements in my field. You can think of those as 2 numbers. What are we going to have? Okay, the first thing is I want you to practice writing these. Notice that we write our vectors, as I have here with the lines over the top, and those are all belong to the set of vectors. And we have the constants a and b, which belong to our field, our underlying field there, F. So you're just practicing writing that out. Okay, so what is a vector space? Well, it's going to be these collections of objects that satisfy a whole bunch of different properties. The first one is that if you have u and v in your vector space, then u plus v must also be in your vector space. Okay? This is called the closure property of that vector addition. Okay? The next closure property is that when we take a scalar and multiply it to a vector v, that also belongs to our vector space. So this property is called the closure property of scalar multiplication. Okay. Well, you'll learn more about that as we go along, but I'm just mentioning, so a vector space has, when we define our addition and our multiplication, they need to be closed, it's called. And then we have these 4 properties. Now these 4 properties are going to seem really similar to some properties you've seen before, and that's because you've worked with vector spaces a whole bunch of times before, but we just haven't called it by that name. Okay. So here are my vector properties for addition. That if we have vector u plus vector v, that's the same thing as vector v plus vector u. That is our commutative property of vector addition. Also, there exists a 0 vector in our vector space, and we write it this way, the 0 with the line over it, that belongs to our vector space, so that when we add the 0 vector to any other vector, we end up with just that original vector. Okay? So we say that this gives us the existence of an additive identity. Then for each vector v in our vector space, there exists a vector negative v in our vector space, so that if we were to add v plus negative v, we end up with the 0 vector. So another way of saying that is that every vector has an additive inverse. We have a final property of vector addition, and that is vector addition is associative. So if I were to take the vectors u plus v, sum them together, and then add that to vector w, what I get is the same thing as if I added together the vector u plus the sum of vector v plus w. So that's my associative property of vector addition. So folks, I know this is a little bit dry, but we have to get through it. And pre-work seems like a better place to do it than in class. And again, what we mean by a vector space is something that satisfies all of the properties that we're listing here. So we have then our 4 scalar properties. The 4 scalar properties say that if we were to take the scalar 1 from our field and we were to scalar multiply it to some vector v, we just end up with the vector v. So this is called the scalar multiplicative identity. That is, when we take the number 1 and multiply it to a vector, we just end up with the same vector. Then we have our 2 distributive laws. This first one will be the, let's go ahead and say what it is first. That keeps me able to write it. This will be the distributive law of scalar multiplication over vector addition. So that says if I were to take the scalar alpha and I were to scalar multiply it to the sum of vector v plus vector u, that gives me the same thing as alpha vector v plus alpha vector u. Okay. We have a second distributive law. This is the distributive law of scalar multiplication over scalar addition. And what that says is if we were to take the sum of the 2 scalars, alpha and beta, and multiply it to our vector, that we end up with alpha vector v plus beta vector v. So we have these 2 different distributive laws for scalar multiplication, and the third one is an associative property for scalar multiplication. So that says if we take alpha times beta vector v, that's the same thing as alpha beta vector v. Folks, I'll give you more room on that when I print it for you. So there are 2 other consequences of this property. The first one is if we take the scalar 0 and multiply it to some vector v, that we end up with the vector 0. Okay. I want you to notice I sometimes mess up my notation here, folks, but I'm being very careful. This is the vector 0, and this is the scalar 0. So, for example, for those of you that worked with vectors in the real numbers, such as R3 or something, if I take the number 0 and multiply it to the vector x1, x2, x3, that gives me the 0 vector. So this is the 0 vector, which is the vector where each of these, in this case, it's where each of those entries are 0. Okay. So I want you to pay attention to the difference between the number 0, which is listed here, and the vector 0, which is listed here. And then we have one other property, and that is just simply that if we were to take -1 times a vector v, that gives us the additive inverse element. So I don't have much more to say on that. Okay. So folks, I find these properties fascinating. They really interest me. They're something that I like to work with a lot. This is kind of getting into what I think of as kind of traditional mathematics. But I could see why this would be very overwhelming at this point. It seems very, very abstract. So let's try to make it a little bit more concrete by coming up with a new vector space. So my guess is most of you have seen this idea of representing vectors as arrows, or you've seen the idea of representing vectors as lists of numbers, but I want to convince you that any collection of objects that satisfies these properties is also considered a vector space, and that's what we're going to do in the next video. So in the next video, you're going to pick up with one of Grant Sanderson's videos and just click that hyperlink there and work through a new type of vector space that you haven't really thought of as a vector space before. And I'll see you then after you complete that page.